Okay, so this is the first in a series of lectures where we're actually going to look at an important area of data loss, leakage and prevention. So in this presentation we'll have a look at some fundamental areas around the security policy, integration, and then on to an important area that we'll see throughout the rest of the units in this course, and that's really how we construct regular expressions. So the main website is here, securitysite.com/DLP. You should find all the videos, the tutorials, and all the related material on that website. Okay, so let's have a quick look at some of the fundamental areas around data loss detection and prevention. So what we have with security is we have our founding principles around C, I and A. So C is the confidentiality, and we use things like encryption and firewall and passwords and so on to be able to make sure that the data itself is confidential and then no one can view it unless they have the rights. Then we have I for integrity. That's all around checksums and hash values and logs and so on to make sure that the data we've actually stored stays as it is and then is controlled as to who is allowed access to it. And finally we have availability, which is looking at backups and failovers and UPS systems and so on to make sure that we have our systems up 24/7. So as part of that, what we have is we have authentication. So we make sure that our users correctly identify themselves onto the network as to their user identification and also their role. Then we have some form of strong access control to make sure that only valid users are allowed onto the system, and then we'll generally audit the events when they are accessing entities across the network. So it could be log on to systems, or it could be access to data and so on. Then we have privacy, which is an important aspect, and that's to make sure that we control the information on the users or the customers that we hold the data on. And then there's non-repudiation, where it's not possible to deny that something actually happened on the network. So let's look at a basic taxonomy for a security incident and see if we can understand some of the terminologies actually used. So normally the starting point is objectives, and that's the reason that someone might want to attack a network or steal data from it. But we'll start from here, and in the first case we have a threat. So that's from a whole lot of different actors, such as vandals or terrorists, spies, hackers and so on. But it could be from an internal threat, and then that threat is achieved by certain attack tools. So there's a whole range of toolkits that someone can use, such as a data tap or using standard toolkits or a script and so on. And then that will exploit a certain vulnerability. So it could be a design vulnerability, configuration or implementation. And with a certain access for files, data in transit, objects in transit, and so on, and then which will result in certain results, such as a disclosure of information, a denial of service, and so on, and then it's for certain objectives. So it might be political gain, or it might be financial gain, or it might be the challenge of it, but generally there is some reason behind why someone would want to steal data from an organization. Okay, so here's a basic definition of our taxonomy for a security incident. A security policy protects an asset in a target of interest in a certain context. A threat may reduce the asset value of an asset in the target of interest and so on. Or a threat may exploit a vulnerability and opens up for a certain risk, which contains a certain likelihood of an unwanted event, which has a certain consequence. So this is the way that we generally try to articulate a security incident in terms of this standard security relationships. This one is based on CORAS, which was a European project. Okay, so what we have, so everything that we do in terms of security should be based on our security policy, and that really fits in with the aims and objectives of the organisation. Any audit, compliance reasons, our legal, moral and social responsibilities as an organisation, and then also it doesn't do any good if it's not actually technically possible, so we need to make sure that what's written in our policy is actually technically feasible. And then we then take our policy and we'll define our implementation. So that might be in terms of operating system rights, domain rights, firewall rules, event logs, and application rights, and so on. It's important that we then evaluate all of these rules and rights to be able to make sure that we validate the security policy against what's actually implemented. So we normally follow some sort of evaluation process. Along with this, we might also have an audit at certain times, and the audit is there to verify that we're actually doing the things that we're meant to be doing. This might go back again to better inform our policy and make sure that we're complying with it, but it also might be to do with an external audit that we have to comply with, and for that reason then we will store the audit information for future purposes. Okay, so there's our security policy. Overall, it's there to deter sort of intruders into a network. It's also there to protect our key assets and our staff. We might also want to define audit and verification parts to our policy, and then some sort of recovery system that we get on, say, if we lost data, and then to be able to react to any threat that actually happens and generally log our information. We have mainly three main parts of that: a general policy defining the organisational roles, disaster recovery, business continuity, and so on. Then we'll also have user policies, which define passwords, internet usage, system usage, and so on. And then our general IT policy, which is really defining our firewall management, updates and mitigation, and so on. So overall, we want really an integrated policy which will actually encapsulate everything that we really need to do. So some of the reasons why we will implement our policy is obviously for audit compliance reasons. So Sarbanes-Oxley is one that related to the auditing of the accounts of companies. So if a company has other organizations inside the US, say, then they must comply with Sarbanes-Oxley's Act. We also have acts such as the Patriot Act, which permits the government to monitor hackers without a warrant. And on the other side, we have the Privacy Act of 1974, which protects the rights of the individual. Then there are a whole lot of other ones, like HIPAA is related to healthcare, and so on. In the UK, we have RIPA, and RIPA allows the law enforcement access to ISP records, but only if they have a warrant. On the other side, we have the Data Protection Act, which is there to protect the rights of the individual for their data. So let's look at data leakage. Okay, so what are some of the things that we want to stop leaking out of our network? Well, obviously usernames and passwords is one. So with the Adobe hack, 150 million passwords were stolen. They were available in hash format, but it was fairly easy for an intruder to be able to reverse engineer these. Where we are just now is between 7 and 8 characters in a password, no matter if they're upper and lowercase, and numbers and so on, can actually be easily reversed from a hash value. So if possible, we should be using 9 characters and more. Credit card details are obviously sensitive information, and we really don't want any information leaking out of the organisation related to that. Intellectual property is also a thing which can be stolen from an organisational infrastructure. And then in a healthcare environment, patient information is obviously very sensitive in terms of the records that the healthcare system has on an individual. Financial information too can give advantages to external stakeholders. If they were to get the early sign of the accounts of a system, they could decide whether they wanted to buy shares or get rid of shares in that company. User activity too is obviously a sensitive thing, so the last thing an organisation wants is to leak information around that type of activity. We might also see the leaking of information around the system configuration, about the Windows domain, and to do with the network infrastructure, and obviously customer details are very sensitive too. But overall, data leakage is really defined as the accidental or unintentional distribution of private or sensitive information to an unauthorized entity. And the losses, there are two really classifications for these. There's direct losses, so that is the loss that can be measured directly after a data leakage event. So that's typically to do with fines from regulators, customer compensation claims, investigation costs, litigation, a hit and reduced sales directly from the event, and also the restoration fees too. In 2010, for example, Zurich UK were hit for a fine of over 2 million after losing 46,000 customer records then. And then more recently, there was an NHS trust which was fined £325,000 for releasing tens of thousands of patient records that had HIV information on them. But there are many other cases which have occurred. One that occurred quite recently was, instead of using BCC, a healthcare authority used the CC field and then included all the recipients involved in related to a health condition. So that meant that all the recipients could actually see all the other people actually involved. And then there are indirect losses, and indirect losses are less tangible, but we can see here in terms of the Target hack, where over 70 million credit cards details were stolen from the point of sale. We can see generally that the share price plummeted directly after the announcement of it, and they've also seen a 50% drop in profit since the incident, which happened in December 2013. So the indirect losses are share price fall, loss of reputation for the company, loss of faith from customers, intellectual property loss to competitors, and one of the worst is the damage to the brand in general. Okay, so it's not just direct losses, it's also indirect losses which can cause a lot of the problem, and data leakage is a very sensitive area and can lead to massive fines and losses overall. So throughout the course we'll be looking at these 4 main areas. So there's the standard security method. So this is really the architecture that we've actually created, our standard security architecture that we can use to be able to monitor for any data leakage, especially with firewalls, intrusion detection systems, antivirus, using thin clients, defining policies, and also domain restrictions. Overall, we're really trying to build up standard fingerprints that we use to be able to detect some sort of data leakage and hopefully prevent it. Along with this, there's better user and customer training is one of the standard training methods that we actually have. In the form of prevention, we need to make sure that we use encryption, strong encryption and access control for all our entities, for all our data, to make sure that that the rights are defined on access and also that the data is kept secure. It's important that we understand the scope of the encryption, because something might be stored on disk and encrypted, but once it goes into memory, it's not encrypted. Once it goes on the network, again, it might not be encrypted, and so on. So the scope of the encryption is very important for us. We'd also might use a rights management system to be able to control the access to all our data. And then the data loss prevention systems themselves will generally look at data in motion, that's network traffic. They'll look at data in use, that's application scanning, and then data at rest, and that's scanning the data storage entities. So with these three, we can really build up a picture of the data as it moves across a network and hopefully detect any loss or prevent it. Then all of these methods might not work together, so we're increasingly looking at more advanced methods, and those are opposed to signature based. We look for more anomaly based. With anomaly based, we look at what's normal and then define when something is abnormal. One of the standard ways of detecting fraud is actually someone working late in the evenings and at the weekends where they've never done that before, and also where they buy expensive goods like a new car or a new house or something like that. Those can be defined as anomalies. Honeypots too can be used, and a honeypot will attract in an intruder into the system. We can have a lightweight honeypot which has very little underneath, or we can have a more heavyweight one which has a whole operating system and entraps the user into them. So things like malware will typically fall into a honeypot quite easily, and we can actually detect it. We often use the first address on a network, say on a secure network, as a honeypot address. In that way, someone phishing for systems will generally find that one first as the most attractive on the whole network, and we can make sure that we detect the maliciousness and keep them away from the main network. Then we might also use activity-based verification, such as keystroke analysis and so on. So it's really looking at some sort of temporal reasoning, machine learning, and so on, to be able to pinpoint any loss of data. So it's these four areas that will actually provide us with the core of the course that we're going to look at. Okay, so there we go. There's our network. It's got all our network components and so on. And our data in motion is really the data that's moving around all the systems, bouncing back and forward and so on, and using all our devices along the way to be able to detect when there has been some sort of leakage of data from the network. Then we can look at data in use. Data in use is where our applications are running, are reading data and then using the data in memory. It might also be sending it over. But this is an important area, and it's often neglected that the data in memory actually is just as open to loss than any other. And then we have data at rest, where the data stops and stays resident. It might be a hard disk, or increasingly some sort of static memory running on a device. Okay, so that's data in motion, data in use, and then data at rest. So if we define for our data loss prevention system, so what state are we looking in? So a data at rest is either local data or it could be remote data. So it could be in the cloud or it could be on network drives and so on. Then there's data in use. We need to understand things like copying and pasting data from one application to another. Also screen capture. Somebody could it might be a predicted document, but they can take a screen capture of it, or also even take a photograph of the screen. Then we have printing. So we need to monitor possibly printers and printing activity to see if someone has printed out sensitive information or sent it over to a fax. There's also the communications that goes on with inside the data in use, and also our application control. Then ourselves, we look at the data in motion. That's the data across the network, looking at well-known protocols, HTTP, FTP, Telnet and so on, but also to look at ones that are less known, such as our malware protocols or peer-to-peer, and generally creating tunnels through the network. What we don't want for data loss prevention is a tunnel that goes from host to host, as we'll see a little bit later, as all our intermediate devices will struggle to actually see any of the data within inside the tunnel. So often within a network, tunneling of data from one host to another is actually barred. Then where do we put the data loss prevention and detection system? Well, we can put them on endpoints on our hosts, and that will be good for our data that's stored on the device and also in memory. But we can also put them on the network, such as within firewalls and IDS systems and so on. And then what's the approach that we're going to take? Are we just detecting the data loss, or are we actually trying to prevent it? So with prevention, we have encryption and strong access control. With detection, we can use context-based inspection. Context-based inspection knows exactly the state that the data access is in. So a typical one with this is firewalls, where the firewall actually knows at what state it's the communication is in, and we'll check the state to make sure that everything is actually correct. Then we can look at content-based inspection. So content-based inspection, we'll have a look at that in more detail. We'll generally look at the actual contents of the data and look for standard signs of any data flow across the network. This is typically looking at things like deep packet inspection. And then there's also content tagging, where we can take our data and then we can add lots of meta tags to make sure that we can actually classify it and detect any leakage. And then finally, what are the actions that we might want to take? We might just want to audit something. We might want to block it. We're going to notify someone that's happened. Might want to even modify what's in the data in some way. Might want to clean it up. If there's a credit card going out on an email, we might want to get rid of it. We might want to encrypt the data, so automatically an encryption method would kick in to make sure the data was actually encrypted before it went out. Or we might even want to quarantine the data for further inspection. So let's look initially at what the data actually looks like, how it's represented, and how we can actually define our signatures. So what we'll find is that regular expressions are used extensively in detecting our data loss. But we'll look at some of the most basic formats first. Okay, so humans understand text typically. So we might start up with our ASCII characters. Those ASCII characters are then represented as some sort of binary format. And then we might take these bit values. Normally they're organized within bytes, and then we might encrypt or encode or something like that. So we end up with another bit stream here. So there are several ways that we can represent that. Obviously one is with ASCII, but often when we're looking at binary data especially, then we end up with a whole lot of non-printing characters. So this one is maybe printable here, but these other ones are not really printable in any sort of form. So the way that we represent them is either with hexadecimal, an octal, or base 64 is our three main methods that we actually use. These are a way that humans can actually interpret the binary data, such as looking for signatures for data, or for things like encryption keys or hash signatures. Okay, so this is the way that hexadecimal works. Hexadecimal, we take 4 bits at a time. So with this we have a 1, a 2, a 4 and an 8 for our bit values. So we just have to count up to 15. So in this case we have a 1 and then we have a 4, which gives us 5 there. Okay, so there's our value there of 5. The next one here is a 2, a 4 and an 8, which is 14. And there's the value here, and so we pick off E and so on. And this gives us our, for this bit stream, this gives us our hexadecimal value, and it's easier for us to remember that or to represent that than it is to write down our binary bit stream. Another method we can use is octal. With octal we take 3 bits at a time, and then we represent them with an octal value, a value from 0 to 7. So if we take an example here of our hexadecimal, so in hex that is a 4. Then the next one is that one, which is an E. And then the next one is an F. And the last one is a 1. So 4EF1 is our representation of that bit stream. Another common format that's used is base 64. So with base 64 what we do is that we want to represent binary values, as we've seen before, in terms of standard ASCII or English language characters. So it lays out a series of characters from A to the slash here, 64 of them, and they're all generally printable characters. So we take 6 bits at a time. Okay, so we take the first 6 here, there we go, and then we take the next 6 and so on. Then we lay these out in groups of 6, and we want to get them into bundles of 24 bits. Okay, so, or 4 of these base 64 characters. So we see here that we haven't managed to fill this last block, so we fill up with zeros, and then there are another 2 that are still empty, so we represent that with a little equal sign. So if we look at it, then here's our first one. We have a 1, a 2 and a 4, 7, and a 16, which is 23. So we look over here and we have 23, so that's an X. Then we do the same, and then we see for this one here, this is the one that we've actually had to modify to add some more zeros to it. That's a 32, and there is the value up here, 32. And then we take the equal signs to make sure that we have groups of 4. So there's a group of 4. We filled up the zeros for the last little bit, and then there's another group of 4. So sometimes we'll have equals and sometimes not, but you'll generally identify base 64 because it has equals at the end. So if we take 3 characters, that's 24 bits, and we've actually managed to fill up all the 6 bits because it's 24, so we don't see the equals at the end. If we took 4 characters, that's 32 bits, 8 each, then we have 30, we have 2 left over, we borrow 4 zeros, and then we've still got 16 bits left, so we end up with 2 equals there. Last one here, 40 bits, because there are 5 of them, That's a 48. We borrow 2, and then we'll take 4 zeros, and there's only 4 bits left now for it, so we only see 1 there. Okay, so generally we'll either see it without the equals, or 1 equals, or 2 equals. That's the general way that it is set up. Or we might even see 3 zeros if there is a little tail that happens after there. Okay, so the other thing we do is that we often take the hash signature of our data. So this gives us a thumbprint that we can actually use. MD5 is a typical one. Unfortunately, it's been compromised recently. It's 128 bits, or 32 of these hex characters. And we take our data, and then we create a hash signature. So this is a file called hello.txt. It's got just the text of hello. We take an MD5 fingerprint of it, and we end up with this data here. And we can also do the same if we have some data. Then we take the MD5 signature, and that gives us that. We can get larger ones. SHA-1 is 160 bits. The longer the hash signature, the more unique it will actually be, and the less chance there is that 2 different bits of data have the same hash signature. Unfortunately, MD5 has been proven that it's fairly easy to actually produce 2 different data values for entities and to create the same MD5 hash signature. Okay, and then we can have SHA-256, SHA-384, and SHA-512. There's a new SHA called SHA-3, which uses a new algorithm just in case a flaw is found in SHA-1. But our focus really is upon our regular expressions, and we need to be able to understand these to be able to see what are to be able to search for data strings in large data sources. So what we've got is that we use the square brackets that will match something. So you sometimes have to do the double slash on a system. When we use Wireshark, we might have to put double slash to represent a single slash because it's an escape character. So in this case, this defines the grouping of the possibilities. So this one here will match grey and grey with an A and an E. We can have a single character within it, and then we can have not, so this will match these ones. And this is a character range. We can go for a character range with inside there. So that will represent from A to Z. And then we can have the number of repeated characters that we're going to match. Okay, and a whole lot of other things here. So we'll have a look at the examples here. So this one, /D, identifies a digit or a number. And this will define 3 digits, followed by a slash or a dot. Okay, so that's 3 digits followed by a dot. There, that's going to match at least from 0 to 1. So there can be no characters there, or 1 or more. And then it'll take, the next thing is 3 numbers, followed by a dot, and then 4 numbers. So that should match a US style telephone number. To match a year, this will define 4 digits from 0 to 9. An email address, a simple one, is any character A to Z, upper or lowercase, 0 to 9. A dot, an underscore, %, plus or a minus, makes up the first part. And then we have an @ followed by something the same. So this will match this part, this will match this part, and then this last part will match that. Then we can have credit cards, so a credit card format. So for MasterCard and Visa, they really just differ in the like a 4 that starts, or a 5. So this is MasterCard here. Then we'll see 3 digits followed by either a space or a hyphen. So there is our hyphen. And then we have 4 digits followed by 4 digits followed by 4 digits. So that gives us that format there. American Express is slightly different. We have 3. It starts with 3, there's 3 digits, and then there's 6 digits after it, and then 5 digits at the end. IP address, fairly simple again. We can look at 3 digits from 0 to 9, a dot, then 3 digits, a dot, 3 digits, and a dot, and then that provides the match there. Okay, so what we're going to do now is that we're going to actually look at a practical tutorial. So have a look at the tutorial that's associated with it, and we'll do some regular expressions from there. Okay, so the next units will look in more detail at that data in motion, data in transit, and data in storage.